Can you hear me? Yeah, I enable mic for all of you. Am I audible to all of you? Hello.
Yes, sir.
Ashish Ranjan, am I audible?
Yes,
Hello.
sir.
Yeah,
Yes,
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 sir.
you're audible.
it is supposed to start from 140 as per
But the voice is little bit low.
Yeah, sir. Your voice is
voice.
very low.
Okay, yeah, just wait. So, no, this session is supposed to start from 140. That's why I was under the impression that it will start from 140. Otherwise, I could have logged in much before. Yeah, is this is my voice clear to you right now? Is that okay?
No, sir, it is
It's
going
lit.
bit low.
Yeah,
Bit
bit
low.
low
What
actually.
else I need to
Still
do?
unclear, sir. We can't hear you.
Is it? One minute. Now, am I now? Now fairly better?
Yeah,
Hello?
it's
Yes,
good
yes.
now.
It's better.
It's good.
Better now. Can I start?
Yes, yes.
Yeah, okay. Yeah, I'm Dr. Gangadhar. So I'll be taking VLSI design for you. And the lab component will be handled by Dr. Naveen. Okay, so I'll be just looking at only theory. And lab, we will start with cadence flow or probably Virtuoso and couple of other tools. Okay. So just make sure before the commencement of every class, make sure recording is on. Okay. Uh, Fine. So let's just go with fundamentals. Let's see now. Okay, let's say, let me try to share my screen. Yeah, let's say so. So let me share my screen. Just make sure whether screen is visible to you or not. Screen. uh, is the screen visible to you?
Yes.
Yeah, is it visible
Yes,
to
sir.
you?
Yes, sir.
Something. Yeah, fine. So no, one thing just would like to, my schedule is, I think it is 140 to, 340. That's why, you know, I just delayed it because I was under the impression that it is from 140. So it has been communicated to you saying that it will start from 130. I just would like to know if it is at 130, I log in at
Yes.
130 from next week onwards. Okay.
Yes, sir. In our
It
calendar, it is one.
it is 130. Okay. Yeah. No. Yeah. Just let it be very clear. That's why. Okay. So this subject is VLSI design, and this course is VLSI design, and course code is VLMZG621. Okay. Uh, so the topics are, let's say, it's a little introduction to VLSI design. It's theoretical in nature, of course. It's completely theory. Different design flows and a couple of issues, if at all, if you have encountered, and what you may encounter. Okay, these are the issues. And let's say in session 2, mass transistor characteristics. Okay, so structures and operation of mass transistors and mass current voltage characteristics, scaling and small geometry effects, and little about MOSFET capacitance. Next is fabrication process and design rules. I'll be just not discussing in detail about it. In lab session, Dr. Naveen is going to discuss in detail about it, and it gets coupled with lab experiments as well, and it will be very clear to you when you do something in lab. So, okay, I'll just touch upon this. Okay. So, and this is more concept intensive. I'll be just discussing in detail about it. And let's say 1 to 4, when I discuss any topic here, let's say, maybe the topic which I need to officially discuss in unit 4, I may discuss in unit 1 or session 1 or session 2. Of course, somewhere it will be covered. Okay, so uh, this is session 4 is all about mass inverter static characteristics. Let's say I think this is the very simple circuit which generally people do know, and that's a very a simple circuit to understand, and it holds good for most of the analysis. So that is inverter. You have pull-up device, a PMOS stuff, and pull down device and mass stuff. The voltage will be pulled down to ground, and PMOS will pull up the voltage to VDD, of course, VDD rail. So accordingly, it gets connected to VDD, and it will charge up to VDD when it gets connected to pull up. Let's say the node gets connected to uh, VDD rail, and when pull down transistor turns on, whatever was charged in terms of the capacitance, that starts discharging towards ground when the pull down transistor turns on for certain gate voltage. Pull down transistor turns on for certain gate voltage, then there is going to be a path which is established that gets completely, if not, it gets discharged towards ground. Okay, so we will just look at it in detail later on. See, that's what is called a CMOS inverter. And along with this inverter, okay, let's see the delay issues. So the delay time definitions, and a couple of other calculations, and detailed inverter design, keeping delay in mind, and how exactly power dissipation is going to dominate if we do not try to look at the voltage, of course. Okay, if we do not try to scale down the voltage, how exactly power dissipation is going to dominate in a design paradigm, that we will see. Okay, and I will just take up these issues probably in today's class as well. Okay, and after this, let's say inverter is a very simple combinational logic. Okay, and in the same line, right? uh, Starting with inverter, we will be looking at a couple of other combinational circuits, in terms of CMOS implementation, full CMOS implementation, let's say. Okay, so let us try to implement that using various topologies. Okay, that's using NMOS load. Okay, and implementing combinational logic using transmission gates and NMOS and PMOS transistors and so on. So implementing any CMOS logic circuit using NMOS, PMOS transistors and CMOS transmission gates. This is about combinational logic circuits. Okay, and next is, as you know, after combinational there is sequential. Again, we do more or less same here. Okay, so we look at timing related aspects of sequential circuits, and a very simple bistable element we look at, and very simple SR latch. Okay, set reset latch, let us try to understand. And afterwards, it's clock latch and flip-flop circuits. Okay, and delatch and edge triggered flip-flops, and latch versus register based pipelines, let's say, and NOR-A CMOS we will be discussing. This is more about sequential aspect of a circuit now. So where setup, hold, clock skew comes into picture. Okay, and you as a student, you must be in a position to draw any schematic for sequential circuit. Okay, and session 8 is all about review. Okay, and now, so this is after this session 8. So pardon me, you're all first semester or second semester? Yeah,
First.
am I audible?
Yeah,
first
first
Yeah,
semester.
yeah.
First semester.
You are you're first semester. I think, hope you all know the rules, right? Yesterday probably you know all the rules, right? Okay, fine. Let's say after this, let's say review session means generally a review will happen, with respect to the topics which were discussed already. let us say, okay, if some topic is not covered, maybe because of a shortage of time, so that topic also can be discussed in review session, and along with that, review of previously discussed topics can happen here. That's what is the meaning of review session. Okay, and sometimes we do get some buffer sessions here. Buffer sessions we do get. So if required, I will just try to look at buffer session as well to cover some of the topics if required. Okay, so next, let's see. After 8th session, you will have mid-sem exam. Hope you know all those things. Am I right? Am I right?
Yeah.
Yes, sir.
Yeah. So you have mid-sem exam. Mid-sem exam. Mid-sem exam is roughly for 30 marks, right? 30% of the weightage is given for mid-sem exam. It is a closed book, am I right? It's a closed book exam. It's like a conventional closed book exam, mid-sem. Okay. So this is for 30 marks. This is called as EC2. Mid-sem is called as, please remember, EC2. And before EC2, generally EC1 will be there. Okay, EC1. EC1 is all about, quizzes and some task you need to complete based on your lab sessions. Okay, maybe you may have to perform some simulation. Okay, that you need to present it. Okay, so maybe some marks will be assigned. That is called as situated learning, of course. Uh, so and in addition to lab, you may have some quiz and you may have some assignment. Okay, so lab session, you may have some assignment from lab, quiz and assignment. All this will be a part of EC1 component. EC1 will have quiz, assignment from theory and assignment from lab. Okay, so lab, Dr. Naveen is going to tell about all those things. Probably I don't know to whom it has been given. Maybe you will just come to know, or I'll come to know after couple of days, of course. So the one who is going to handle the lab will look at all these things, lab exercises and all. You will have to simulate and you have to take uh, snippet of it and it has to be submitted. Okay, well within the deadline. Please, all of you follow the deadline. Don't keep sending your assignments after the deadline to my email ID. I may also miss because I'll be getting 200, 300 mails every day. I may not be able to check. To look at 300, 200 emails, at least I need 3, 4 hours. No, I think it may not be possible. That is why all of you please meet the deadline. Okay, so don't wait till the end of the deadline. Try to complete before that. Please don't send any assignments to my email ID. Please avoid it. Okay, so it becomes very difficult later. You say I have sent it and it has not been valued. Of course, assignments must not be sent through email. Okay, it should be uploaded in a proper portal. Okay, all that links, everything will be given to you well in advance. Okay, so that's about EC1. Okay, please, all of you make sure don't send assignment through email. You please submit before the deadline, right, to the proper portal. Okay, so let us say now review will happen here in 8th session. After 8th session, you will have exam. You will have mid-sem regular exam and you will have mid-sem makeup exam. Okay, and afterwards 9th session will start, that is dynamic logic circuit. So we will be looking at past transistor circuits, bootstrapping and synchronous dynamic circuit techniques. Okay, and also we will be looking at high performance dynamic logic CMOS circuits. Okay, so that is dynamic logic circuits. And again in session 10 we look at low power aspects of VLSI design. So why a circuit will draw higher power, in what way we can reduce the power consumption of that particular system or design. So overview of power consumption, low power design, or how exactly we can achieve low power design, if at all, if I concentrate here on the low power design. So what are the steps we can take? Okay, so capacitance. Yeah, am I audible to all of you? Hello?
Yes,
Hello?
now.
Yeah. So power dissipation also depends on capacitance. If possible, is it really possible to reduce the capacitance to meet the power budget? And the last topic here is adiabatic logic circuits. Okay. And next is interconnect parasitics. Let's say we do connect, you know, different transistors together. Okay, so when we connect different transistors together, so is that interconnection which we use to connect different transistors together, is that interconnect is going to exhibit some amount of resistance, capacitance and inductance? Okay, so all those things are called as parasitics. You know, you have capacitance, you have resistance, you have inductance. Let us look at all those effects, of course, and how exactly an interconnect can be modeled electrically. So the interconnect looks like lump Darcy transmission line where it is going to be terminated by a impedance, right? So how exactly we can reduce all these things keeping delay in mind? So we'll be discussing all these things in detail during session 11. Okay, and clock signal generation and clock distribution. How exactly clock signal can be generated and distributed so that design works perfectly fine under all circumstances. So this leads to timing classification in digital systems. And again, little about synchronous design and timing basics, like again, setup, hold, clock, skew, jitter, so on. Okay, there is, something like clock distribution. And, we will be talking about latch based clocking as well. And afterwards here we have design of VLSI arithmetic circuits. So as you all know, digital circuit is divided into data path and control path logic. Okay, so we will be looking more often about data path in this context. So data path in digital processors and different adder architectures and different multipliers like that are various other multiplier architectures, a booth, so on. So and there is a shifter. Let's look at shifter architecture as well. Okay. uh, a lot of analysis is really required when we look at low power aspect, right? A lot of things like Shannon's expansion theorem and all that. Okay, so we will just discuss all those things. Next session 14 is all about memory design. So as you know, we have RAM, static RAM, dynamic RAM, and peripheral circuits related to memory, of course. So we'll be discussing all these things in session 14 and how exactly validation can happen, right? Validation and test of manufactured circuits. It's about fault types and models, controllability, observability, ad hoc testable design techniques, scan based techniques, and BIST. Okay, so and this is about session 15, and session 16 is again a review session. If some topic is left out, right, and that topic can be discussed here, or otherwise if every topic is already covered, so review of all these topics can happen in this session. Okay, so this is about theory, and the book which you can refer here is, let's say, uh this is the textbook. This is a pretty good book. First one covers, I think, not all the topics, couple of topics, and this also covers couple of timing related issues, setup, old clock, skew, jitter, all those things are pretty good in Rabe and Ananta. You can have a look at it, and other dynamic logic circuits and power related issues to some extent are there in Kang. And in addition to this, I do refer 1 minute. See, this is CMOS logic circuit design Oyemura, and there is another title by the same author, John P. Oyemura, and I think it is. I don't remember right now the exact title, but the contents are more or less same, right? So that is some digital VLSI system design, something like that. Same author. Contents more or less are same. So I may refer that book. You can refer that as well. And the same content you see in this book also. Only the title is different. So fine. So I want content, not the title. Okay. So, and this is also pretty good book to go through if you are starting, something for the first time in VLSI. I personally recommend this CMOS logic circuit design, or another book. I think VLSI system design, something like that, by same author, John P. Wyamura. It's really a good book to start with, and the flow is good, English is good, you can understand better, of course. Okay, you have very simple math, easily you can digest. Okay, it's relatively a good book to start with, of course. And once you are comfortable, you can look at all these things. Kang is relatively, you can start with Kang as well, of course. And this is, this is kind of concept intensive, Ananta. It's also pretty good book, of course. Okay. And whatever the material I give, sounds good, keeping all these contents in mind. Yeah, this is about uh, the course handout. Yeah, anything else would you like to ask? You can please ask me. Yes. uh, I know if anybody knows the total number. Anybody knows total number of students here? No, no idea. Yes. Fine. Now let us say the very first topic. No, I just before I start, let us say CMOS. What exactly is CMOS? Any guess? Yeah. Let me ask you guys. Uh, Session one. Yeah. All these things are, theoretical in nature. 1 minute. Let me just. Issues. Okay. Fine. So let's say, just let me try to take up something which is very relevant. Uh, okay. Just wait for some time. Yeah, just look at it. So this is, let's say, so I think even, okay. Yeah, just 1 minute. Look for another flow, I think. Okay. I think this is better. I think. Yeah, let's see now. Uh, whatever, let's say, we do, whatever we do, that should have a methodology in VLSI. Of course, there is a specification for a system. Okay. So we need to look at functional aspect of it for the specification. Okay, so that is called as a system specification. So we need to look that specification from functional aspects of it. Mean to say, we need to look at that specification. What should be the architecture really required to meet those functional recs, okay, or functional requirements. So again, let's say there is a functional design now. So let us say I have made, or I have expected, or I am expecting something out of this, and let's say that is being designed here, that's already designed. Now whatever has been designed here, is it really according to my requirement? Okay, so that we need to check here. Is that according to my requirement? That I need to check. Okay, I think this is the one. Okay, yeah, just so now let's say we have mentioned the functionality here. So generally what we do, we use hardware descriptive languages. No, I think one thing I would like to ask you, I think yesterday I think today morning you had 8:20 to 10:20, you had a class from Venkat, right? Guys, today
Yes, yes,
morning
Yes, sir.
you had a class CAD for VLSI, right?
right.
Yeah, I think Venkat has discussed about all these things, if I am right. Yes or no? This flow. Okay. So again, let's say, the next week, the CAD also I am going to take 2 sessions. I am going to take CAD. Yeah. Okay. And this flow is common everywhere, of course. Yeah, please understand. Now I'll be discussing about HDLs there in another course for you only. Okay. So this is what is a functional design. Here HDLs will come into picture. The popular HDLs which are used nowadays are Verilog and System Verilog SV. And some defense organizations do use VHDL even today. I don't know why, of course, because they have a lot of they have a lot of restrictions. Okay, but this Verilog and System Verilog are very you know popular hardware descriptive languages. And another interesting story most of you might be knowing, SV is used to carry out verification before. Now this is also emerging as a powerful synthesis language. This is also emerging nowadays as powerful synthesis language, but before this was a powerful verification language. Now this is becoming powerful synthesis language as well. In other words, what I am trying to tell you, even to write a RTL code, people nowadays started using SV long back. Since 2 3 years, people are extensively using this SV to write RTL code. But before, Verilog was used to write RTL code. So something RTL, okay, RTL means register transfer level. Okay, see, this RTL is something which goes and sits inside silicon. So if you write some functionality using RTL, right, it will be in sync with silicon. Means when you say I'm trying to tape out a chip, that taped out chip will have the functionality which is specified at RTL level. The taped out chip will have the functionality, and that functionality is specified using RTL. There is something like would like to add here itself. So there I will just cut down this discussion. So if I say RTL, it is something which can be synthesized. Please understand. This is something which can be synthesized. What does it really mean? Any guess? Because so RTL is something which can be synthesized. RTL is something which can be converted to gate level netlist. What is RTL? RTL is something which can be converted to gate level netlist. Please understand. So this gate level netlist again, so we will have to look at floor planning. A PD guy will come and he looks at all those things. Let's not worry about all those at this point of time. Now let's say RTL can be converted to equivalent gate level netlist by synthesis. When once I fire synthesis, the higher level abstraction gets converted into lower level abstraction. The higher level abstraction is Verilog SV VHDL and lower level is gate level netlist. This is a gate level netlist. So let us say now, before I convert this into gate level netlist, I have my RTL code. Let's say I have RTL code. I do not know whether RTL code meets my functional regs or not. I need to run verification. I need to run verification. Okay. In order to verify that whether my functionality is going to be met or not against the test scenarios or test cases. So I think probably you might be knowing SV UVM. So UVM is a methodology. So those things are used in order to carry out this task. This is functional verification. Let's say functionally, if it is all right, functionally it is all right, we try to fire synthesis. When once synthesis is fired, whatever RTL I see here, whatever RTL I see here, so for that you will see equivalent gate level netlist. So that equivalent gate level netlist is called as logic design. Here that is called as logic design. So again, yeah, guys, you please understand. So once verification engine, ends, DB guy is sitting here, verification engineer is sitting here. He says this is okay, and this all the tests are passed. But when once, let us say, when once I fire synthesis, so I have equivalent gate level netlist. It doesn't mean that again also it is functionally all right. I need to run it again. I need to verify it again. You got it? I need to verify this again. This is called as logic verification. Let's say again a PD guy will come and do P&R and he'll try to place and route the signals to meet all the budgets. So again, when once he does his job, after that he will get one netlist. Even that also has to be verified against functionality. Again, DV guy will come there. Design verification engineer will come there. So let's say you have a circuit now. When once I have done with the logic verification, you have a circuit. Let's say when you have a circuit, okay, the circuit also has to be verified. The circuit also has to be verified. So this results in PD, of course. This is, physical design. Again, this results in physical design. Again, let's say, there is a layout. All the transistors are connected together inside a chip. So every transistor is having its own layout, let us say. So I'm not really touching upon various cells and cell-based designs at this point of time. Let's say you have different transistors which are connected together. Every transistor will have its own layout, and all those layouts needs to be verified. That results in layout verification. If it is done properly, right, it is good. If there is any bug, again you need to go for this design and then you have to redo it, of course. So everywhere, if there is some bug here, you have to go back and fix it. Let's say if it is not functionally all right, go back and fix it here. Fix the bug here. Let's say if it is not logically all right, go back and fix here again. So if it is all right, go for circuit design. Let's say functionally, if it is all right, go for synthesis. Okay. So now try to verify the circuit. Try to verify the circuit. If it is not all right, go back and fix it. So if it is functionally all right, go for PD. Okay. So again, there is a PD, you have a layout, you try to verify that layout. Let's say if the test is not passed, go back and try to fix the bug. So finally it goes for fabrication and testing now. So this is how typical flow looks like. Okay. See here in my course here, I will not be discussing anything about HDLs, but in my course that's CAD for VLSI, I'll be discussing about, uh, a Verilog, of course, if possible, would like to look at the system Verilog, so because time is not sufficient there also. So but definitely I'll be discussing Verilog, okay, there. So, and we will be doing a simple verification, not using UVM because in 1 hour, 2 hour, I cannot look at it. So we go for test bench using Verilog there. We go for test bench using Verilog. Test bench using Verilog, and we try to do all these things using cadence flow probably. I think it is cadence flow. Cadence flow. So I think we use ESCLZG from cadence there. ESCLZG. Okay, see this is so this one. This is my part there, and again Venkat will come for this. It's called a synthesis, and again I will be coming here, of course. Part of circuit verification and physical design. I'll be coming here. I'll be coming here. So now my course, this VLSI design, is more or less concerned with this portion again. It is more or less it has topics related to circuit and physical design, of course, but we don't call it as directly physical design, but it has a lot of issues or a lot of topics which are very much essential for you to understand physical design. Okay, so it's about transistors and its layouts. Okay, so and extraction of parasitics, all those things we do come into picture. Yeah, any doubts? Any doubts? If you have any doubt, please feel free to ask me. Yes.
Hello.
Yeah, please.
Sir, actually, one subject you were referring right just now, some other subject.
Ah, yeah.
So actually, we are from embedded system, means MTech embedded system. We are currently in second semester, and we have opted for this VLSI course, and we don't have access to that Verilog subject. So
Okay, no problem. No. You don't worry about it. I think a couple of other students. I think this is. I feel this is a merged class or something. It doesn't affect
yes,
you.
sir.
You don't worry about it. You don't worry about it. And if you look at this as a whole, okay. See, this is a typical design flow. You see, this course does not require these things. Whatever I said, functionality, right? Functional verification, logic design. Logic design is definitely involved, but you need not have to know HDL as far as this course content is concerned. You don't worry about it, because there are a couple of students who are there for that course also. For them, I have discussed. And if you know this, it's really good, of course. This is a typical flow. So it doesn't affect you, of course. You need not have to worry about it. Whatever is really required, that I'll be discussing. You don't worry about it. You got it?
Okay, sir. Thank you.
Yeah. That's
Hello.
it. Yeah, yeah, please.
Sir, one quick question.
Yeah.
So in the layout verification, right?
Mhm.
If something is wrong,
Mm.
so we are going to fix in again physical design phase only. But I feel it should go back to the again the uh like design functional verification, because the parasitics will comes.
Yeah,
This will
yeah,
alter
yeah.
the that arrow is missing, or
No. See, this functional verification here, it's only at the highest level of abstraction we do look at it, of course. Now we
okay.
have English specification that will be converted into, uh, coding based stuff, of course. I have English specification, let us say. For that, I write a code in HDL using Verilog or VHDL or SVV, write it. Okay. So if something goes wrong, we go here from here there. From year to year we go if something goes wrong. But if something happens here, see, I need not have to go there. So I'll have to go back here and try to fix it. Okay.
Okay.
Yeah. Any other doubts? Anyhow,
Hello, sir.
yeah.
This logic verification and layout verification, is it related to LEC?
Yeah, definitely.
Okay, these checks are like LEC only, right? We are doing
So no,
RTL2.
you are no, again, wait. You are from which embedded system? Just now, one of
No,
your
I'm from
friend has.
PD.
You are from PD. I think LEC, there is, but LEC I'll not be discussing here. I think CAD for VLSI design, no? CAD for VLSI design as LEC, of course. There is one script they run, okay,
Okay.
for LEC. Okay.
Okay. Then
So,
what we
no, but
check in
one
this
minute,
layout
one minute, one
verification?
minute. Probably, I think LEC is different and LVS is different. You are talking about LVS, if I am right. Is
No,
that
I'm
right?
talking about LEC only.
LEC
So
only.
LEC
Okay.
will check logical equivalence check, right?
That,
LBS will
yeah,
check
yeah.
for shorts and opens.
Yeah. No, logical equivalence makes sense here, of course, in front end part, of course. Here, it gets coupled along with RTL design in most of the cases. I think Venkat, maybe not in this subject. I will not be discussing about LEC at all. Logical equivalence check, I will not be looking at it, of course. Okay, because
Okay.
this course is all about with respect to transistors. It's all about more or less it is coupled with physical design, of course. Okay.
Okay.
So,
Okay, sir. Thank you.
definitely, I'm sure, I think you'll be doing LVS and extraction, RC extraction and all that you'll be doing it, of course. That's for sure. But LEC in this course, I think no. But if you belongs to another one, let's say, I don't know, you belongs to embedded system or something like that, but definitely, I think Venkat is going to, run one script for logical equivalence check, of course. I think that what happened, we were doing it before. Now we had 8 lab sessions. Now it has been reduced to 5. Hope you are able to understand. So I remember we did it. you know, uh, I think now I do not know, but yes, we have done LEC when we started this course. I think we were having 8 lab sessions. We used to get a lot of time, a lot of bandwidth. But yes, LEC is part of front end flow, of course. Yeah. Yeah. Any other doubts?
No.
Yeah. Okay, fine. So now let us say, I think, did I answer all your queries, if at all? Okay, now let us say, so the very first, some mathematical equations directly I will write, because, okay, yeah, this is what I have discussed using different PPT or slide deck. Of course, conveys more or less same information. Okay. Mm, it's okay, fine. So let's say now, so uh, so at design abstraction levels, if I look at design abstraction level, I have a system. You please understand, I have a system. Assume the system looks like this. Inside a system, you have different modules. Inside a module, let us say you have gates. Yeah, you please understand. So even in this course, I don't even look at this module. Okay, generally module is coupled or it is in sync with hardware descriptive language. So now, so my discussion starts from here. Let us say my discussion starts from here. 1 minute. Snip, right? So yeah, see, this module. It is coupled with Verilog or SV or anything like that. So when once you fire synthesis, we will end up with all these things. So we will have gates. So it is, it's the complete thing we are discussing is CMOS. It is CMOS. So every gate, as you know, every gate will have transistors. Every gate will have transistors. So of course, this is not a representation for this. Please don't be under that impression. It is generally written like this. This is more specifically, if I am right, it is an inverter. It is inverter or NOR gate, what you have studied long ago. If you are not working in this domain, it is inverter or NOT gate. Okay, let's see, I have an inverter. Okay, this inverter, assume this inverter as PMOS device. This is my PMOS device. This is my NMOS device. See, this PMOS device, let us say, is called as pull up. It is called as pull up, or you may have more than one PMOS devices. Then it is called as pull up network. If you have more than one, we call it as a network. It is pull up network because this pulls up this node to VDD. Let's say this is VDD. It is not written there. This pulls up the voltage to VDD. And again, this is called as, you may have one or more than one here. This is called as pull down network. These things are extremely important for my discussion. That's why I'm trying to pitch all those things here. It is called as pull down network. So because here the voltage is pulled down to ground. This is ground. The voltage is pulled down to ground. Please understand this now. These are extremely important. These topics are extremely important for you to understand my next contents. Okay, so now let us say, so okay, let it be here. Now every transistor, what I said here, PMOS, every transistor, what I said here, PMOS and NMOS, PMOS, PMOS will have its own layout. No, because there are other students also, because I will have to speak in a language which they also can understand. So PMOS is a transistor. Let's say it's a PMOS transistor. It has its own layout. Please understand. Now something like layout you understand, don't worry. You will be understanding that uh, in detail in future sessions. PMOS. This is PMOS. And NMOS is another transistor which is sitting below here, below. This also has its own layout. Please understand. Okay, this also will have its own layout. And if you look at physical cross section, yeah, please understand. If you look at physical cross section, let's say, if you look at the geometry, see a transistor looks like this in silicon. Let's say with respect to silicon, the transistor looks like this. Yeah, you please understand now. Okay, so this is source, this is drain. N plus is something like heavily doped. Doping concentration is slightly more. Okay, that is why plus is used. It is more. Or people do say heavily doped. Okay, or it's doped heavily. So hope is it clear? This is a convention which is being used here, of course. So now plus is just that. So yeah, 1 minute. So now see this circuit. Let's say the circuit is now at silicon level now. So this is a transistor. This is a transistor which looks like this, physically. See, the question is, so when this CMOS transistor was invented, any guess when this CMOS transistor was invented? Yeah, yeah, I'm just asking you casually. Any guess when this was invented? No, now another question is this invented before BJT or after BJT?
After BJT.
After BJT? No, it's just casually I'm asking. Yeah, please. Just to understand how things were developed in the beginning.
I think first year BJT only, then this.
No. This is, I think BJT was somewhere developed and tested probably in, maybe during 45 to 47 in that duration. In that
Bell
duration.
Laboratory that was.
Yeah, absolutely. So, but no, around 1930s or 35, let us say, this CMOS was invented. Please understand, this was invented and people were not aware about the better aspects of this CMOS, hence they did not use it extensively, of course. CMOS was not used extensively, though it was invented before BJT was invented. Of course, somewhere accidentally one guy was working with the CMOS and accidentally came to know about, the better power dissipation capabilities at that time, not now. And then, it became popular. Okay, though it was invented much before BJT was invented, people were not really aware about the capabilities of a CMOS logic. Okay, so keeping this in mind, let us say what I'm trying to pitch at this point of time is, let us say you have gate here, you just go through it, you just try to go through it 2-3 minutes, 2-3 minutes, just go through it. So yeah, let us say so this is C. So it is called as C because it is complementary. As you know, let us say if I give 0, this transistor is on. Please understand, this transistor is off. Okay. If I give 1, this transistor is on, this transistor is off. So they are complementary. Complementary signals will turn on these two devices, hence it is complementary. Complementary. Yeah, please understand. So I think you know there is one terminal like gate, right? There is one terminal like gate, right? Yes or no? This is gate. It is like a tap, water tap. You know, if you just vary the tap position, you can increase the water flow or you can decrease the water flow. So like this, you can use this gate voltage to increase the current or to decrease the current. Am I right? It is like a kind of regulation. So, and you can control the flow of current just by varying the voltage applied to the gate terminal of a transistor. Yeah, you please understand. Okay, so now let's say, now I think there is a terminal called gate. Gate is made up of what? Generally, gate is made up of what? So, you know, why I am asking, I should know, you know, how I should correlate. Okay, a couple of concepts based on your background. That's why I'm asking. It is not to discourage you. Please don't be under that impression. Yeah, there is a terminal called gate. Gate is made up of what?
Metal.
Any guess? Poly. Yeah, yeah. Metal. I'll come back. It is called as poly. Generally, that is what is pronounced more in literature. Polysilicon, right? It is poly. So, you know, fortunately or unfortunately, when this CMOS was invented, gate was realized using metal. When this was invented, gate was realized using metal. Metal was used as a gate. Later on, that metal is replaced by poly. Please understand. So that is why even today people do use metal. Though you don't see metal here. You have metal, but not here. Okay. So now this is my gate. This is my gate. Just below this gate, I have oxide. Let's say to understand SiO2, let's say silicon dioxide. This is a SiO2. And this everything is built on silicon substrate. This is built on silicon substrate. So this is built on semiconductor. So complementary metal oxide semiconductor. S stands for semiconductor. It is built on semiconductor. Let us say it is a semiconductor device. And again, it is CMOS, or there is another word people do use. Please understand. MOSFET. Heard about it? MOSFET. Because this analysis is extremely important for my discussion. That is why I'm discussing. It is also called as CMOSFET, or people do say simply MOSFET. MOSFET. What is MOSFET now? So as you know, it is metal. O stands for oxide. O stands for oxide. S stands for semiconductor. This is built on the semiconductor substrate. This is built on semiconductor substrate, hence it is called as semiconductor. So it is called as field. Okay. What do you mean by field? Is it electric field? Is it electric field? Yeah, guys, please understand.
Yes,
Is
yes.
it electric field? Okay, fine. So there is a electric field. Yeah, fine. Let us say. So understand, we apply some voltage here. Gate voltage we apply. Let's say I call this as VG. Yeah. And so I'll try to bring up a mathematical model here itself, if possible. Okay. Let's say I apply a gate voltage. Let's say if I apply a gate voltage here, what will happen? Let's say this is N. This is supposed to be P. This is how, fabrication happens. This is P. Now let us say I have holes here, but I have electrons here. Now let's say I want to have a channel. I want to have a connectivity from source and drain. Means in place of holes, I should have electrons. Then only I can have channel. So in place of holes, I should have electrons. I should apply appropriate voltage here just to attract electrons here. I should attract electrons here, and in place of holes I should see electrons. So this will happen if I apply certain polarity voltage to the gate terminal of a transistor. Assume now, please try to understand this concept. Assume now, in place of holes here, let's say I have holes here, holes I write it as P. In place of holes, assume I have electrons. Now let's say I have electrons here. So now there is a channel here. There is a channel now. Now see, it is something like, let's say I have a channel. Do you think current is flowing now? Do you think there is a flow of current from one terminal to another terminal? Source is one terminal, drain is another terminal, gate is another terminal. Okay, bulk is another terminal. Let me not come to bulk at this point of time because that is not that relevant. Of course it is relevant. It is basically a 4-terminal device. It's not a 3-terminal device, but for most of the digital applications 3 terminals are okay. But yes, bulk is also extremely important now. Yeah, so another simple question which I asked you is, let us say I have created a channel now. So can we expect current flow through this channel at this point of time as it is? Yes?
No.
It is like, let us
If
say,
inversion layer formed, then it will.
Pardon me.
If it is inversion layer, if it formed,
Okay.
then
No.
current will start.
No. Let's say you have inversion layer now. Yeah, this is what is inversion layer. I have not yet told. I thought I can tell later on. Now let us say this is what is inversion layer. Where I had P, in that place I have N now. Where I had holes, I have electrons now. This is called as inversion. The charges are inverted. So we say inversion. There is an inversion with respect to charges. Hence it is called as charge inversion. We call this as charge inversion. Is this clear now? So assume charge inversion is already happened. There is a charge inversion already. Understand? Now it is like, let us say I want to move from Bangalore to Chennai. I have a car and there is a road. So now I have a road and I have a car, but I don't have driver. Let us say. So can I reach? Assume this is not a driverless car. Let's say driver is required. Assume can I reach Chennai? That's a question now because I need driver, let's say. Okay, so now what I am trying to tell now is I have a channel now. Yes, I have charge carriers. So when do I say current is flowing through the device? So I'm really talking in terms of very simple stuff. Of course, I don't want to introduce too much of VLSI at this point of time because so I think we do have people from embedded domain as well. You also should feel comfortable. Okay, now let us say I want to have current. What exactly is current? Yeah, in physics, how do you what do you mean by current now in physics definition? Let's say I have, yeah, very good. Rate of change of, absolutely. Let us say, okay, yeah, very good. Is it something like dq by dt? Can I write like this?
Yes.
Now, what does it really mean? So mathematically I write like this. What does it really mean? Let's say, is it a measure of movement of charges over a period of time? Let's say some charges are moving in 1 second. Yes or no? That is what is the physical meaning of dq by dt, right? How many charges are moving in a given time? So let's say now, can I say I can expect current if and only if charges are moving? Only moving charges will contribute towards current flow. Am I right? Is that true?
Yes.
Yeah, please
Yes.
understand. Please understand. Is that true? Let's say the moving charges will contribute towards current. Yes or no? They only will contribute. And that only will be treated as a current, in other words. So now let us say, what should I do now? What should I do? Now, yes, I do have charges, but are they moving now? The question is, are they moving? Here, assume I have charges here now. I have electrons here. Assume charge inversion is already happened here. There is a charge inversion. Means, let's say there is a road which exists between Chennai and Bangalore, let's say. You got it now. So now what should I do? Come on.
Potential difference. Okay.
Yeah, absolutely, I should have a difference. You are absolutely right. Let us say now, you think, assume I ground this source terminal. Let's not worry about this source terminal. Okay. So now let's say I apply certain voltage to the drain terminal. Let's say I apply certain voltage. Assume I apply positive voltage to the drain terminal. Now, like charges attracts, unlike charges repel. Yes or no? So now can we try to attract these electrons from source to drain? Can we try to attract these electrons from source to drain? Yeah, please.
Yes.
Yes. Yes. Now, when I try to apply this voltage, I'm trying to attract these charge carriers from source to drain. So can I see movement of charge carriers now? No, see now your dq by dt will come into picture now. Please understand. So this makes sense now in this scenario. So can I say these charge carriers are moving? Yes or no? Yeah, please understand. Yes or no? These charge
Yes.
carriers are moving now. These charges are moving. When charges are moving, it contributes current. It gives me current. So this current I call it as ID. This current I call it as ID. Now let us say. So now you please understand. I increase the magnitude of this positive voltage. Let us say, yeah, you please understand this voltage which I apply to this drain terminal. Let's say I call it as VDS. I call it as VDS. So now I increase the value of VDS. Can I expect more current? Can I sweep or can I attract more number of charge carriers from source to drain? Yeah, please, I want you to interact. Otherwise,
Yes.
yes,
Yes.
yes or no? You think logically. Yes,
Yes.
yes, fine, very good. You are absolutely right. Now let us say, so when I apply voltage, can I say I am or this device is under the influence of electric field?
Yes.
Can I say? Huh?
Yes.
Yes. Okay. Oh, fine. Now I'll come back. You know mass so far. Mass. Let's say there is one thing called F. There is one thing called E. Fe, that is field effect. When I apply a voltage, we can always expect electric field. Yes or no? There is always a electric field. Definitely there is a effect of electric field under this circumstance. There is electric field which is going to be available here. It is going to be available here just because of the application of two voltages, one to the gate terminal and another to the drain terminal. Let us say if you apply one voltage, you will have one electric field. If you apply another voltage, you will have one more electric field. Totally, you have two electric field components. Yeah, please understand this. No, if you understand this, you will definitely, you can understand today's challenges when you go to, nanometer regime or angstrom regime. What are the problems which we may have to face in future in terms of, device fabrication? Okay, so can I say now I am applying two voltages here? Yeah, please understand. I'm applying two voltages. Can I expect two electric field components? Yeah. If you say yes, then only I will proceed. Huh? Yes.
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 So now let us say I apply voltage to the gate terminal. You got it. Can I say just because of this, I can expect vertical electric field component? Vertical electric field component. I write it as VEF. Vertical electric field component. And let's say I apply voltage to the drain terminal. Can I say it results in horizontal electric field component? Horizontal electric field component. Yes. Come on.
Yes.
Yes. Now let us say all these charge carriers, please follow this flow. All these charge carriers are under the influence of, or under the tremendous influence of two electric fields which are produced because of the voltage applied at gate and drain terminals. Am I right? Am I right? So that is why it is called as field effect transistor. Transistor is basically a switch. A switch can be on or off. Okay, that is why it is called as FE, field effect. There is a strong influence of this electric field. Only under the influence of this electric field, all these charge carriers will move from one terminal to another terminal. Is this clear now? Is this clear? Yes or no?
Yes.
Yes,
Yeah.
sir.
Now what I do, see, there is a derivation for this. I don't go for, I think there is a derivation probably. I generally don't want to derive something which has been already derived. Okay. So, but I definitely use this derivation for my discussion. You got it? Let's say, no, I can start with fundamental physics concepts and we can derive. That's not a big deal, of course. Now, when once, let us say, I derive this, it looks like this. I think I may need, okay, let me derive, let me delete couple of these stuffs now. So all of you must understand now that, see, all these charge carriers are under the influence of strong electric field produced because of the voltage applied at gate and drain terminal. This you should understand at this point of time. Now let us say, so I increase this voltage applied to the drain terminal. What will happen to the electric field? Electric field increases. Let's say if voltage increases, E is V by D, physics formula. I studied long back, of course, maybe 10th or 8th or 9th or somewhere. So if V is increased, of course, if D, distance of separation, is constant, so my electric field also increases, derived from physics, of course. So now, let's say if my V is increased, my electric field is increased. What happens if electric field is increased? The charges which are sitting here will become highly energetic. Please understand, they'll become highly energetic. All these charge carriers will become highly energetic because they are under the influence of strong electric field. Please understand. So when they are highly energetic, please understand, some of the charge carriers will try to break this oxide region. Can I expect this? Can I expect this?
Yes.
Yes.
Some of the charge carriers will move in random direction because they are highly energetic charge carriers now. Please understand, now the situation is different. See, this is a major challenge which we are facing now when we try to reduce the distance, because we are trying to minimize the total area occupied by a transistor. So hence, obviously, the channel length also is getting reduced, right? So depending on new technologies which are emerging, right? For every process node, we do look at it, of course. Let us say I'm trying to reduce this distance now. When I reduce it, so, electric, you will see strong electric field and all these charge carriers will become highly energetic. Hence, they try to move in random direction. During this time, they try to break this oxide. This whole process or mechanism is called as oxide breakdown. Oxide breakdown. Is it really required? Oxide breakdown. So it breaks the oxide. Okay. So what happens just because of this, some charge carriers will enter this region and they will be trapped here. They will be trapped here. Some charge carriers will break this oxide and they get trapped here. They get trapped here. All these kinds of trapped charge carriers will redefine the threshold of the device. Hope you know there is something like threshold for this device. Let's say it is VTH. This is the minimum voltage which is really required to establish the channel, or in other words, this is the minimum voltage which is really required to switch on the transistor. So VTH is the minimum voltage. Now just before VTH, you do see the movement of charge carriers, but it is very less, of course. We say it is weak inversion. So now if you slightly increase the voltage above VTH, we say it is strong inversion. Strong inversion, charge inversion it is basically. So if the applied voltage is slightly less than VTH, we say there is still a inversion, but it is weak inversion. So this is, if the applied voltage is equal to VTH, we say it is okay inversion or simply inversion. That's it. Now this is a notion, of course, which is being used here, of course. Is this clear? So now let us say there is something like mu. What is this mu? Mobility. So they all will move. They have mobility. Okay. So let's say now directly I will write this mathematical equation, let us say. So now let us say, now under this scenario, the current which flows from one terminal, maybe from source to drain or drain to source, anything, no problem. Let's say I call this as IDS. IDS is equal to mu n. What is this? Mobility of charge carriers. Mu n, n stands for electrons, mobility of electrons, mu n. Cox, this is oxide capacitance. This is oxide. It results in some capacitance. I call it a Cox. Cox. And W, this is the width of this width, and this is the length of the channel. Width and length of the channel. Okay. Width and length of the device, let us say, width and length. Okay. And then let us say, understand these three, let us say, they are process dependent parameters, of course. So they are process dependent parameters. Process dependent, let us say. So now let us say, now you come back to the voltage part, let us say. So this is VGS minus VTH. Yeah, please understand now. So whatever VTH which appears here, that amount of voltage I'm going to lose because I need to overcome that voltage level. So, let's say I apply VGS, entire VGS will not be useful for me because I am going to lose the threshold part of it here because of this charge inversion. I need to overcome the voltage, of course, here. So that is why. So whatever the effective voltage which comes out here is VGS minus VTH. This I'm going to lose. That's why I'm using minus sign here. VGS minus VTH. I will not get completely VGS. So I'm going to lose VTH because I'll have to overcome that barrier now. So to overcome that barrier, I'm going to lose this threshold. So I call it as now. So this is VD. As I said, I apply voltage to the drain terminal. I call this as VDS. VDS. It's a standard, standard way of representing these parameters. I say it is VDS. Please understand. Minus of V square ds. So this you can derive. I am not deriving it directly. I am writing it. Yeah, please understand. So ID is equal to IDS is equal to mu n Cox W by L VGS minus VTH VDS minus of V square ds. See, I think you are studying analog IC, right? Analog IC design, right? Yeah. Tell me yes. So I think you are referring a book called Razavi. You are referring a book called Razavi, right?
Yes, sir.
So better, for this derivation, you refer this book. He has illustrated the concepts beautifully, of course. So very technically beautiful, and you will understand most of the things. Okay, Razavi is a Bible, of course, for most of the concepts related to transistors. Okay, yeah, you please refer Razavi. I do refer that for all these topics, of course, but it is completely towards analog. But this you can pitch to digital as well. Only these topics you can pitch for digital VLSI as well. But here all my discussions are with respect to digital flow, not analog flow. But Razavi will focus on analog flow, of course. But this is okay, of course. So now let us say mathematically how it looks like. Okay, I think I will have to draw this again. Okay, no, fine. Okay, let's say now I need some space here. Okay, now, so as I said, IDS is equal to, okay, IDS is equal to mu n Cox W by L VGS minus VTH into VDS minus of V square ds. So, mathematically how it looks like, let us say, yeah, please understand. Let's say, I think, hope there is x-axis and y-axis. Let's say x-axis I use VDS, a parameter called VDS here, and y-axis I use, what shall I use? Let's say IDS or ID or whatever. Now, if you look at this behavior, how it looks like? Any guess? Come on. So initially the current is 0. If you keep on increasing VDS, what will happen? If you keep on increasing, what will happen?
ID also increase.
ID also increases. See, it looks like this. As per that equation, it looks like this. This is the equation for parabola. Again, it drops. It reaches peak, but we don't want this to happen, of course. We don't want this to happen. We would like to maintain it constant. Whatever was the peak, we would like to maintain it. This is what is IV characteristics. We are not really interested in this. This is called as parabola that mathematically represents parabola. Now let us say, so this is my VDS. This concept is required for my discussion somewhere. So this is VDS, this is ID. Now let us say, so as I said, this is the peak. No, mathematically you can derive when the peak of the current occurs. You need to differentiate it and equate it to 0 mathematically. So now this peak current will flow through the device when VDS hits the voltage. When VDS hits the voltage, VGS minus VTH. When VDS hits VGS minus VTH, then maximum current flows through the device. Hope you are able to understand. Okay, so this is called as ID max. So when VDS, let's say VDS is 0, some voltage, at some point of time, VDS turns out to be VGS minus VTH. So when the applied voltage is equal to VGS minus VTH, maximum current flows through the device. So now let us see what will be the current flow when VGS minus VTH is reached with respect to VDS voltage. Let's say now I have this expression mu n C arcs W by L. I have this. It is VGS minus VTH into VDS minus half V square ds. Now let's say what I said, what will happen to VDS? VDS turns out to be VGS minus VTH. This turns out to be mu n C arcs W by L. Okay. This is VGS minus VTH. In VDS turns out to be again VGS minus VTH minus half. VDS is again VGS minus VTH whole square. VGS minus VTH whole square. This is a very important relationship which is really required for most of the VLSI related subjects. So this is now, it is VGS minus VTH, VGS minus VTH. It is VGS minus VTH whole square minus half VGS minus VTH whole square. If you take VGS minus VTH whole square common, you will end up with 1 minus half VGS minus VTH whole square. 1 minus half is half. Very simple substitution. Very simple manipulation, of course. So this is, you will get half now here. Because of this half, it is VGS minus VTH whole square. I write that half here. Please understand. I write that half here. It is mu n C arcs W by L VGS minus VTH whole square. Understood? So now can I say this is the maximum current? This is the maximum current. When you apply VDS, which is equal to VGS minus VTH, we say the transistor is saturated. We say the transistor is saturated. Saturated means what? The current will not increase again, even if you increase what? Even if you increase VDS. So means no more it is a linear device. No more the relationship is going to be linear. Generally, let's say here, is this linear relationship more or less? Not exactly. Is it linear? Come on.
Yes.
Yes. What do you mean by linear? Let us say, no, see some straight line. Let's say, look at it, some straight line. This is linear. If this guy is increasing, this guy is also increasing, by some factor. Are you able to understand? So though it is not exactly straight line, you can approximate it as a straight line. This is linear here. But when once, let us say, peak of the current hits this, Let's say afterwards, is it linear? No. Even if you increase your VDS, my IDS is not going to increase the way I increase VDS. Hence, it is not a linear device from here onwards. It is only linear in this range. It completely becomes non-linear. Now, sometimes non-linearity is also important, but sometimes non-linearity is not important. So, depending on that, we need to play with the device. So now, what is the
So,
current?
sir, here ID become constant, right?
ID?
ID become constant, na?
Yeah, when once it hits the VGS minus VTH regime. Yeah. Yeah, of course, no. Literally, it should become constant, but even then, it is not constant. Slowly, it varies. There exists a slope. Yeah, it's a right question. Let's say here, you asked here, right? It increases like this. It hits this peak, and here it becomes constant. Is this your question?
Yes.
Here. Yeah, it should be constant, but what happens, no? It should be constant literally, but because of various effects, so you will have slope, some finite slope you will have. So, because look at it. So if it is something like this, I say it is constant. Am I right? Am I right? Let's
Yes.
say. So, but what happens, no? Strictly speaking, it will be something like this, something like this. You will see a very small slope here. So, this gives me a line now. It's not supposed to be a line. Just wait. Wait, I'll just, shall I delete all these things? I'll delete. Okay. So essentially, you expect it to be like this, right now. So what happens now? Here you will see some significant slope here. It will be like this. There will be some small slope here. Okay, slowly it varies because of various other second order effects like channel length modulation, body effect, subthreshold conduction. There is some small amount of conduction do happens even when you don't hit threshold voltage level. Just because of those things, there you will see a minor variation. It's not too significant, of course, but literally it should be constant. It should be like this. It should be like this, literally, in ideal scenarios. But you will see some slope even today, like this. Slowly it varies. Okay, with respect to VDS. Yeah, did I answer your question?
Yes, sir. Thank you.
Yeah. Bye. So, this is, sorry, this is ID or IDS, both the same, let's say now. So no, for me, at least, no, you should know why I am discussing about this device, because this is a device which is used for all computations. You look at any laptop, you look at anything in this universe, if it is electronic system, it will have transistors. Okay, so that is why we need to understand about transistors. Okay, and its connections and what really happens if you go for long interconnect, what really happens if you go for short interconnect. So is that delay going to be impacted just because of this interconnects and all that? Now, let's say when ID is equal to, half ID or IDS, both are same. Don't worry. No, don't get, don't be confused if I write IDS in place of ID or something like that. Both are same, of course. Of mu n C ox W by L VGS minus, I use some terms here and there. I just would like to write all those terms now, because you must not think something else when I use them. Okay. So this thing, right? So now see, for a given transistor, this mu n is fixed and Cox is fixed. Okay. And let's say when once it is available in standard cell, or when once it is available in library, all these things are fixed. The only thing is I'll just pick and I'll use them. So, what is important now? Let's say, this is square of the voltage. See, this VGS minus VTH is called as overdrive voltage. I'll be using this word, overdrive voltage. This is called as overdrive voltage. Or it is also called as what? Only VGS minus VTH I am telling, not square. It is also called as R, effective voltage. Or effective voltage. Or effective voltage. Okay. Any doubts here? Yeah, if you have any doubts, please let me know. effective voltage. No, hence it is called as a square law device because current varies with respect to square of this. So now see, now you understand. I'll just try to sync this concept with something else, and that is very important in the context of VLSI design. Okay, let us say now we are all aware that power dissipation is something which is going to impact. Okay, let's say power dissipation P des, I say it is P des, power dissipation is equal to alpha, please understand, alpha, okay, times F times square of the voltage. So look at it. It is something like VGS minus VTH, but I write it as V square. Okay, V square D or whatever. And C, I call it as CL, let us say. This is a combined capacitance, of course. It may incur this CX as well. Please understand. Okay, so now what happens in this case? Let us say if I increase voltage, what will happen to the power dissipation? Come on, what will happen to the power dissipation? If I increase voltage, what will happen to the power dissipation?
Power dissipation also
Increases. In what rate it increases is a big question which needs to be answered now. Let us say somewhere when people started using mobiles, right? Probably I remember the scenario in 97. In 97, I think the chips which were sitting inside the mobile were using 5 volts, if I am right. More or less 5 volts, I think I'm sure, right? Yeah, you please understand. 5 volts. So what could be the power dissipation those days, let us say? P des is supposed to be, I don't touch rest of the parameters. Let's say 5 square is 25. Yeah, you please understand. Rest of the parameters, I keep it as it is. F alpha, FCL. Is this clear now? Let's see now, today, we are using a voltage which is less than 1 volt. Let's not worry about less than 1 volt. Let us say it is definitely scaled down to 1 volt. Let us say, assume, so my v square turns out to be 1 times alpha FCL. Yeah, you please understand now. I am trying to scale the voltage from 5 volts, let's say, to 1 volt. Maybe this 1 volt was there, maybe somewhere 2021, of course, or 21, 22 somewhere. See, 97 to 21 approximately. Just see, we have taken so many years to scale the voltage from 5 volts to 1 volt. See, but so what is the impact with respect to power dissipation? Power is dissipated by 25x. You could realize 25x improvement with respect to power dissipation. See what I am telling now, the computations are increased. I'm not really keeping those things in mind. No, only for a given computation we need to look at this. Now mobile is not just a mobile. You can do a lot of other computations. You have so many cores over there to do a lot of other stuffs for us. Okay, so now let's say if I don't scale the voltage, power dissipation increases like anything because this varies with respect to square of the supply voltage. See, these things are also very important in one of the session, probably low power. In low power, I think you will have to answer this. Am I audible? Am I audible? Yeah, please, guys, please respond. Am I audible?
Yes,
Yeah,
sir.
now audible.
Yes.
Yeah, fine.
You're audible,
So,
sir.
yeah, please understand, if I don't scale the voltage, just see how much I need to pay for power dissipation. Hope you are able to understand. Let us see, I have a transistor. So the transistor is designed to operate at 5 volts. The same transistor will not give me the same rec if I reduce the voltage to 1 volt. It doesn't even work. Hope you are all aware. You got it? Now, let's say to get the same behavior from the same transistor, even if I reduce the voltage to 1 volt, the transistor needs to be redesigned completely. it's a different engineering, of course, very tough engineering problem it is, of course, but it has taken so many years. You please understand, reducing voltage and on top of it, so the transistor must behave properly, right? So it has taken so many years, no? Everything has to be redesigned, right? So it requires a lot of engineering, of course. So this is R&D, of course. So this is how power dissipation can be decreased by scaling the voltage. Okay. Now on top of it, let us say now. So even here, let us say if I increase voltage, let's say P, let us say if you increase voltage, right? So power is proportional to voltage now. So it dissipates more power. Both are true, of course. So now, so what is the other parameter now? No, because only a PD guy can look at it, of course. CL, others may not be able to play any role over here, of course. Let's say I have some capacitive load. There is so much of capacitance in a chip. Okay. So, if you can reduce it, obviously you are contributing towards this power dissipation, of course. Means your circuit is going to dissipate, or your system SOC is going to dissipate lesser power. If you have an opportunity, you can try to reduce the power dissipation by reducing this CL now. Okay, so but let us say, there is a slogan in VLSI: faster circuits are always power hungry circuits. Faster circuits are always power hungry circuits. When do we say the circuit is fast? So if frequency is more, we do say the circuit is faster. When frequency is more, the power dissipation is also more. If frequency increases, power dissipation increases. Yeah, you please understand, this is the relationship. If frequency increases, power dissipation increases. See, but increased frequency makes us happy, but at the same time, increased power dissipation does not make us happy. Is that clear? So we do say there is a trade-off between power and performance. Frequency is generally attributed as performance. Performance is measured, measured with respect to frequency, or rather, let's say, uh, okay. So frequency, it is coined towards performance, let's say. Now we do say there is a trade-off between this power and performance. This frequency is the performance. There is a trade-off between power and performance. Is that clear? Yeah, anybody? So, this I'll not be discussing in detail. Now only I am discussing. Okay, I'll not be discussing this in detail. So, but we do really need this knowledge. Okay, so to solve couple of numericals, probably I think in session 11, if I am right. Okay, 10 or 11, I'm not very sure. It's, when we look at low power design related issues, we need to see, other probabilistic models more specifically. So, all the tools, uses those concepts in order to give you a power report. When you ask the tool to pitch power report, when you try to look at the power report, indirectly it will be going through different probabilistic models. They're all coded in higher level languages. Accordingly, it will just get the power report, of course. So only thing we will read and, try to take corrective measure in order to keep, the power dissipation within our budget. So that's how things will happen, of course, but things are available to us readily. So, but all the algorithms are going to be implemented using these concepts. Okay. Yeah, any doubts? So now,
Sir,
any doubts
power
now?
dissipation,
Yeah.
if it is come, then activity factor also play major role, right?
Definitely. Yeah, I'm about to start activity factor now. Yeah, I think most of the other factors I discussed it. Definitely, you are absolutely right. Activity factor. So another important parameter, uh, as it was told just now, is activity factor. It's more specifically alpha. More specifically, alpha is called as, I just erase it, alpha. So in P, power dissipation, this alpha is called as switching activity factor. Yeah, I'll just give you one simple example. Please understand. This is switching activity factor. Only RTL guy can control it to some extent. RTL guy can control it in the beginning. Switching activity factor, if possible, again, of course. Switching activity factor. No, only at, a micro architecture level, one can think of, uh, reducing the power dissipation just because of this activity factor, if possible. If possible, let's say now, what does this activity factor mean? Okay, let us say I have a task. I have a task. That task requires, let's say, it's a clocked, a clocked circuit is really required to achieve that task. Let's say, assume functionally, if you look at that task requires 4 states. Yeah, please understand 4 states. This is my reset state to start with. Let's say this is something like S0 and this is S1. To understand the concept, to S2, S3. Let's say this is how my functionality is defined. This is my requirement. Okay, functional requirement is just this now. Yeah, please understand now. Let us say, this is the functionality. Okay, now I need to implement this. When I look at implementation, let's say now, no chips can understand S0, S1, S2, S3, so on. Okay, it's only zeros and ones. So let us say when I go for implementation, S0, I encode it as 0, 0, understand. S1, I encode it as 0, 1. S2, I encode it as 1, 0. This is usual gray sequence, of course. Sorry, binary sequence. S3, I encode it as 1, 1. Understood? Okay. So yeah, fine. So now let us say this is one scenario. Assume I get the functionality, right functionality. See, whatever I do, I should get the same functionality. That is mandatory. Whatever I do, you got it, no? So now let us say, instead of going for this S0, please understand, I go for 0, 0. Again, same thing. I don't change here. Let's say here, I keep same thing here also, but here I make it 1, 1. Please understand. Now here I make it 1, 0. And again, let us say, and again, so from S3, let us say I'm coming back to S0. See, from S3, please understand, we are coming back to S0. That is the behavior. See here also, from S3, I'm going back to S0. So here also, this is my S3. Again, I'm coming back to S0. See, there is no space. Please understand S0. Now, which one you feel is better in terms of power optimization? Let's say, when I say power optimization, my circuit should dissipate lesser power. When I ask the tool to optimize this with respect to power, it will look at all these things, in what way it can make it viable in terms of less power. So now tell me manually, which encoding here, which encoding is really good in terms of power optimization?
S0 or S1?
Second
It
one.
was
Yep. Which one? The first one or second one?
Second one. Second one.
Second one.
Second one. How do you say second one?
The number of switchings are happening less.
Switching.
Yes, less number of switching activity you see here. Let us say now, okay, to understand, absolutely second is the right option. Let's say alpha, if I look at it, let's say when you move from year to year, when you switch from this state to this state, how many transitions you see here? It is 1, is it not? From 0, 1 to 1, 0, how many activity you see here? How many switching you see here? 2. 1 is changed to 0, 0 is changed to 1. So from year to year, again you see 1, 1, 0 to 1, 1. Some 1, 1 back to 0, 0, again you will see 2. So totally you have how many? Let's say my alpha is 6. Is this clear to all of you? Yeah, come on, tell me. Is this clear?
Yes, sir.
Now, let's say you look at the other encoding. So 0, 0 to 0, 1, 1. So 0, 1 to 1, 1, what? 1. 1, 1 to 1, 0, what? 1. 1, 0 to 0, 0, what? What? How much? How many bits are changing when you go from 1, 0 to 0, 0? 1. So what is alpha now?
4.
4. So no, this is the first case. My power dissipation is alpha times 6 times F V square C CL, whatever. So second case, let's say I call the first one as P1, second is P2. This is 4 times F V square CL. Simple. Now same thing is true even for today's complex SOC. The concept remains same. Only thing is number is more. That's all. You will see more number of switching activities because you will see more number of transistors, of course. Okay, but definitely it is true in silicon, of course. For silicon substrate, absolutely it is true even today. Okay, so let us say sometimes we will create a scenario to have this, right? And you will have to take a call on how much power you are going to reduce, how much power, what factor of power can be saved if you go for different encoding. So you will have to think and answer. Okay, so such questions will be asked definitely, and these concepts are extremely important for you to understand typical VLSI design flow and to face, I think midsem and comprehensive exams, that is EC2 and EC3. Okay, yeah, any doubt here? If you have any doubt, yeah, please ask me. No, today I started 6 minutes late, so I will continue uh, till 1:36. Yes or no? So from next week onwards, I'll start from 1:30 only. Okay, so now any doubt here? What is really important, I will just discuss. See, this is a typical flow. VLSI design flow. You have a system spec, functional design, functional verification, logic verification, circuit design, circuit verification, physical design, physical verification. So this whole flow is called as front end. This second one is called as back end. It's more or less, finally we end up with layout, of course. Okay, this is all theory. Easily, if required, I will discuss again. Okay, in the next class. So okay, see, as I already started pitching towards power, let me try to look at that again. Let's say. So let's look at power dissipation in detail now. So instantaneous power, PFT it's P is equal to, as you know, well-known mathematical model. It is P is equal to V into I. So if it varies over a period of time, let us say instantaneous, if you look at, you pitch T all the time. It is P of T is equal to V of T, I of T. Let's say what is V of T? It is a supply voltage. V supply into I of T. Okay, what is the peak power? P peak is V supply and I supply. Power is maximum when current is maximum. Simple. What is the average power? P average is 1 by T. So try to integrate all the power. Try to add all the power in this particular range, in this particular duration. Let us say that duration is capital T. That's the meaning of this integration. 1 by T and divide it by T. It is like averaging it. You got it, no? Yeah, guys, I'll ask you one question. If you are from digital, or digital, let's say if you are from front end, what does it really mean? Let's say if I want to go for this implementation digitally, how will you do it? How will you implement it? Yeah, let us say if this is the case. Yeah, let's say I just wanted to go for integrating something with respect to T, let us say, or over a period of time, whatever is there in certain time duration, I would like to integrate it. What does it really mean, integration? Come on. So integration, let's say in analog domain, is equivalent to what in digital domain? Any guess? Because otherwise you cannot go for implementation in digital domain. What is this?
Summation.
Summation.
Integration.
Absolutely, right? No, rather than summation, yeah, the concept is absolutely very close. Can I call it as accumulation? It is called as accumulation, or accumulator. You might have heard about it. Accumulator, right? So this is analogous to accumulator in digital domain. What is that I am trying to do? Let us say I add everything. Of course, I add everything and I divide it by T. That T is a duration now. I'll get average power. That's all. As simple as that. Okay. So this is Now let us say average power is 1 by T integration T to T plus capital T PT dt. This is equal to, let us say, I take out, V supply here. Let's say PFT, I write it as V supply I peak or V supply IFT, anything of course. Okay. So I write this as V supply. This one I just pitch here. It is V supply. I take V supply is a constant. I take it outside because integration allows that. So IFT, I can write it as I supply FT or simply IFT also you can write it. So this is my average power. Okay. Okay. Now power delay product, it is PDP. This is equal to, right? Let us say it is P average into TP. It is P average into TP. So energy delay product EDP is equal to, it's a quality metric of a gate, of course, just to have a metric with respect to the quality of a gate, we do use these parameters. So quality metric of a gate is E into TP. It is E into TP. Okay. Let us say, we do call this as a first order RC network. So there is one resistance and there is one capacitance. This is a RC network and it is excited by some input. It is, more often, let me call it as, I trigger this guy. I trigger this guy by uh, a pulse, let's say. I pulse. So I call this as first order RC network because I have one resistance and one capacitance. Let us look at energy dissipated when the signal is making a transition from 0 to 1. Let's say the total time duration is T. I just look at 0 to T. I start from 0 and I end with the T. I accumulate all the power. Let's say that's the meaning. I accumulate all the power in that particular duration T, that is P of T dt. That's accumulation, or it's accumulator in digital domain. Let us say mathematically if I want to write it. Yeah, please understand. Mathematically if I want to pitch, P is equal to VI. So what is V? V is VDD or V supply. Anything you write, no problem. Because I pasted from a different source. That's why he has used VDD. No problem. You can use V supply also. Don't get confused. Whatever V supply, whatever you see here, you can put V supply here also or VDD also. No problem. Okay. I don't go by all those things. I just would like to check concept. That's all. VDD into I supply of T dt. Let's say VDD is constant. I take it outside. Okay. Okay. Then what about this? I is equal to, see now, this is VDD. Finally, it is CL dV out. Any guess? I is equal to, yeah, come on, can you tell me how to go about it? Now there is suddenly there is a new relationship now. If you can tell. And it is not, something unknown to you at this point of time. No. If it is something unknown, I will never ask you. Let us say I is equal to C, is it dV by dt? This is the equation. I is equal to C dV by dt. Okay.
Yes.
You got it, no? This is what I just expected from you.
Yeah.
That's it. No problem. Okay. Think studied long back. True. Okay. See, this
Yeah,
is
correct.
just pitch that here. You try to pitch that here. So you finally get this. Let's say you will get half CL VDD square if you consider one cycle. If you consider another cycle, it is half plus half. It becomes 1. That's what we are trying to pitch 1 here. Means it is CL VDD square. Is this clear? Are you able to understand? See, see, this is DT, right? DT, right? So see here, you don't see T here, you see V out because I just put that in place of C. I supply of T, I put, shall I do this or is that okay for you? Will you understand? If you want, I can do it. Okay. Fine, no problem. So what is important for me, you should understand. That's what is important. It is VDD. Let's say I just look at a interval from 0 to VDD. I change, we call it as limits of integration. No, even I also studied long back. 0 to VDD. It is, let us say I, C is what? CL. Yes or no? I, dV. What is V here? V is V out, right? See, I is equal to, I change it according to my requirement. C dV by dt now. Look at it. dV by dt now. So what is I now? Okay. So I is I supply of T, let us say. It is I supply of T. I write it as I supply. This C is what here? What is this C? Come on, CL. I want you to interact. CL. So what is V? V is V out. Simple. Now I just plug in that here. CL dV out by dt times dt. So then you will end up with VDD. You will end up with VDD 0 to VDD CL dV out. CL dV out. Are you able to understand? Yeah, please. So now let us say this is, I take CL out. Let's say my VDD out. Let's say now this turns out to be V out. Integration of dV out is V out in the interval 0 to VDD. What is this now? It is CL VDD. What VDD? It is V out VDD minus 0. Yes or no? I think you remember integration?
Yes.
It has been a long time for you, right? Okay, no problem. So this is VDD minus 0. It is VDD. It is CL what? VDD square. This gives you the total energy, of course. Okay, this is CL. I think this is what? Okay, shall I rub this? Now, let us say, so energy with respect to capacitor, let's say, I do say P cap, power dissipated with respect to capacitance. Let's say this is 0 to T. P cap is I out VI. P is VI, right? This P is VI. Understand? VI. So this V, I am writing it as what? What is V? V sounds to be or looks to be V out, and I sounds to be here. Let's say I cap of T. It's lowercase or uppercase. No issues. I cap of T, because T means my current also varies over time. That's the meaning. So it may decay also. That's why T is. I'm trying to plug in T here. So this is what you see this now. Okay. So now it is, let's say now I just change the limits of integration now, let's say, because in place of T, I just plug in, V out, what we have seen, I is equal to C dV by dt. I is equal to C dV by dt. So that is why V comes here. That's why I'm trying to change the limits of integration, of course. There is a computation in integration. How do you change limits of integration? Let me not go to that extent. Let's say for me, the voltage range is 0 to VDD. I cannot go beyond it. Let's say my range is 0 to VDD. I just look at that. Okay. So now what happens is, yeah, please understand now. It is, you have CL constant here, please understand. So now you have V out here, V out. So V out dV out. Okay, just see, I'll just delete a couple of things. See, this is what we have now. Yeah. So I want to integrate this. Let's say I write here, this is CL integration of V out. Let's say it is V square out by 2. If I am right, it is V square out by 2 in the range 0 to VDD. Okay, lowercase VDD. Okay, so this 2 I'll take it outside. It is CL by 2 it is, let us say, VDD square minus 0. This is I write this 2 as 1 by 2, 1 by 2. I write this VDD square minus 0 is VDD square times CL or half CL VDD square. So this is how it can be derived, of course. So again, this is for one cycle, charging and discharging. Discharging, if you look at, you will get the same thing. If you add these two, the total stuff sounds to be 1 V square DD. That's what you see here. Okay. Okay. So no, these are all, I think easy to understand. Let's say 1 minute. Okay. Yeah. Let's say what's important in my context. I will just look at it. Just right. Yeah. Let's say now, in the context of circuit design, okay, let's see, what we can do. The purpose of the circuit design is to develop a circuit representation based on the logic design. Whatever the logic I have, for that logic, I have to design a circuit. Okay, see now, the Boolean expression can be converted into a circuit representation. The Boolean expression, whatever you have, that gives you a logic, and the logic can be converted into equivalent circuit by taking into consideration the speed and power requirements of the design. Okay, we need to design the circuit which includes gates, transistors, interconnections, etc. And all these connections, gates, transistors, interconnections, generally it is called as a gate level netlist. So we try to carry out simulation to verify the behavior at circuit level. So circuit simulation is used to verify the correctness of the particular circuit and its associated timing related issues. Okay, just design verification. Okay, let's see what are the issues in digital integrated circuit design. So the key issue whenever we look at IC design includes power dissipation. Just now we have discussed, and just because of power dissipation, you do see thermal management. Power dissipation, right, increases the temperature. Okay, so that is why that increased temperature is a thermal issue that has to be managed properly. Okay, so speed and power performance optimization is extremely crucial, and see that increases design complexity and verification related issues, and also manufacturing becomes a bit challenging, with respect to leakage and variabilities. So designer must also ensure reliability. So the designer should ensure reliability by managing factors like electromigration and noise. And let's say the designer should be in a position to navigate the difficulty of integrating certain functions on the same chip. Let's say it's a problem of mixed signal. Let's say you'll have digital part and analog part, and the digital stuff must talk to analog stuff, and the analog stuff must talk to digital stuff. Even in spite of that, there should be a reliability, of course, right? And one should, a designer must be in a position to manage electromigration related issues and noise related stuffs. Okay, so a couple of other issues related in digital IC design are performance and speed. Speed and performance, if you look at, designer must ensure faster switching speeds. This is what I have discussed so far. That's why I'm going fast. So designer must ensure faster switching speeds, and he must ensure higher data throughput. Higher data throughput is a measure of number of tasks which can be performed in a given time. So let's say if I say throughput is more, so number of computations are more in a given time. Okay, so this is challenging. This is challenging, and it becomes too complicated as the complexity of the circuit design increases. So there is another important thing one should know is critical path. The entire speed of a design really depends on the delay of this critical path or length of this critical path. So the delay through the longest path in the circuit is a major factor to decide the speed. This needs to be minimized. The critical path needs to be minimized through proper design techniques. Okay. So, it is as illustrated in example of carry lookup adder. Of course, it's a carry chain which turns out to be a critical path in that context. Power and thermal issues. So if you look at power efficiency, reduce power consumption. Just now I have discussed a lot about power consumption. Reducing power dissipation or power consumption is very crucial to prevent overheating. Unless you adapt a technique to reduce the power dissipation, you cannot reduce the heating. So it gets heated up and eventually the chip may fail at any point of time. So that is a question of longevity. Of course, you cannot even predict the lifetime of a particular chip. If it gets heated again and again, definitely the lifetime has to suffer just because of this heating. So when this gets heated up, if the power dissipation or power consumption increases, then it gets heated up. So this is very important to decide the life of a particular chip. Let's say power efficiency, reducing power consumption is crucial to prevent overheating and extend battery life in most of the mobile devices. So heat dissipation, the energy dissipated by transistors and interconnects must be managed to prevent damage to the chip. If the dissipation by transistor and interconnect is not managed, then eventually it may result in failure of the chip. It may not work the way we want it to work. So, a lot of power is being consumed by clock because clock undergoes various transitions, 0, 1, 0, 1, 0, 1. So most of the power, generally, literally, roughly 35 to 40% of the total power is being consumed by clock itself, because we cannot do anything without clock, of course. So that is called as clock tree power. This is coupled with CTS, clock tree synthesis. So hence it is called as clock tree. Clock tree power. So, we will be discussing about this in, I think, session 12 or so. The clock distribution network can consume a significant amount of power. There is a network which can distribute the clock so that all the flip-flops can get the clock more or less at the same time. So this whole mechanism is called as, or the process is called as CTS. It is clock tree synthesis. Okay. So summary, how much time? 36. Yes, perfect timing closure, right? Yes. So summary, digital integrated circuits have a long way and still have quite potential left for the coming decades. Some interesting challenges are ahead. So we need to have a clear perspective on the challenges, and we should come out with potential solutions, right? To make the circuit viable in terms of non-functional requirements like speed, area, and power. Okay. Of this book means, those things are written, of course. Understand the design metrics. We need to understand the design metrics, with respect to the digital design flow. Understanding the design metrics is extremely crucial. What are the design metrics? Design metrics are something related to cost of the circuit, reliability of the circuit, speed with which the circuit is going to operate, and the power the chip can consume, and the energy it is going to dissipate. These are all the design metrics, and a designer should really understand all these design metrics when he goes for a design. Yeah, if you have any doubts, please feel free to ask me. Yes. Yeah, if you have something to ask, you can ask me. So otherwise, I can wind up. So shall I? Shall I?
Sir, two questions.
Yeah, please.
So today, what I understood is like we are somewhere is like kind of overview of VLSI design we are going through, right?
No, it is a first unit, of course. I mean, first session, of course. Yeah, it is there in the syllabus also. I would just discuss what is there in the syllabus. Okay. Yeah, it is overview, kind of overview. You are right. Absolutely right. Yeah.
Yeah.
Did I
Actually,
answer your question?
I request like when we go for the next session, right? If we get some material, which we are
Yeah.
going to
No.
discuss.
I will be uploading. I will upload. Okay. Yeah, just
No. What
definitely
I'm
it will be.
saying is before
Okay, got it.
this
Got it.
So we can come with a preparation with a mini question.
Okay. Yeah, we'll do it. No, I'll upload all the session PPT. Is it okay? Forget about one or two session. I'll upload all PPTs in one shot. You can go through everything. Is that okay?
Yeah, that is okay.
Yeah, sure. Yeah, did I answer your question? Fine. Yeah. Any other questions?
So for now, what you have explained in this class for the basics, can we refer, as you mentioned, the textbook called Razavi's one?
No, but see, Razavi, only the transistor related parameter you look
derivation.
at. Razavi.
Oh, fine.
Okay, only transistor, because I'll tell you, Razavi is a very fantastic book for analog design. Okay, no, it's a Bible, of course. It's a very good book, no doubt, but not for digital. The flow is different for digital flow. Okay, but somewhere we do have something like second order effects like channel length modulation, body effect, subthreshold conduction, that is very well defined or very well explained in Razavi. For those topics and whatever I have discussed, I think probably I'll be discussing that again, maybe somewhere about that derivation. I need to discuss in depth again. For those things you can refer Razavi. It's up to you, but it's not mentioned here. It is, you can have a look at it, of course.
Okay, like power dissipation for that.
No. Power dissipation is not there. It is not there in Razavi. It is. Yeah, please.
But what textbooks can we refer for that?
No. That is there in all the books. Kang, I said, Kang and Y.M. Mura and I think Ananta Chandrakasan. It is there in all the books. Got it?
Okay.
It is there in all the books. Right. Okay. Yeah. Oh, shall I log out? Shall I quit this meet? Okay. If you have anything, you ask me, or else we'll see you in the next session. Okay. Yeah. Bye.
Thank you, sir.
Yeah. Bye.